It's the first week of March 2026, and looking at the raw data right in front of us, the weather is it's completely undeniably broken.
It really is.
We are currently staring at a map that makes absolutely no logical sense whatsoever. On one side of the country, people are sweltering through 106-degree heat in what is technically still the dead of winter. It's dangerous, blistering midsummer heat.
Right.
And yet, on the exact opposite side of the country, entire communities are currently paralyzed, buried under historic blizzards with emergency crews working around the clock. It is an absolute atmospheric traffic jam out there. Today, our mission is to untangle this bizarre global weather map and figure out exactly what the science says is driving these massive extremes as we transition into spring. Welcome to Meteorology Matters, the podcast that dives deep into the science, chaos, and stories behind the weather that shapes our world. This show was created by meteorologist Rob Jones. Now let's get into today's episode of Meteorology Matters.
It is truly a wild time to be looking at the atmosphere, and I'm really looking forward to breaking all of this down for you today.
Before we jump into the sheer chaos of this data, we want to take a quick second to ask you to please like, follow, comment, and rate the podcast wherever you are listening. Taking a few seconds to do that really helps us bring this research to more people who want to understand what is happening in the sky above them.
Absolutely.
Also, make sure you follow meteorologist Rob Jones across social media. You can find him on Instagram at the handle meteorologist, on TikTok at TV Meteorologist, and on YouTube at Rob Jones Hurricane, where you can also find the full Meteorology Matters podcast playlist.
What's fascinating here is how the atmosphere right now is essentially acting like a massive battleground. When you look at the research we've compiled, we have entirely conflicting seasons fighting for dominance across the continent. And, the stakes for the people living under these systems are incredibly high.
That is the perfect way to frame it, a battleground. To give you a roadmap of where we are heading today, we are going to start by covering those shattered temperature records out west, really looking at the mechanics of that heat.
Physics of it, yeah.
Exactly. Then we are going to look way up high into the atmosphere to understand the bizarre, lazy behavior of the jet stream right now. From there, we will break down a severe storm threat that is actively drawing dangerous moisture from the Gulf of Mexico.
Which is a huge concern.
A massive concern. And finally, we will zoom out to the global level, look at the fading La Niña, and discuss a rather startling 5-year global climate forecast that has just been released by the research.
It is a massive amount of ground to cover. But understanding the why behind the weather outside your window, rather than just the what, has really never been more critical for your daily life.
Okay, let's unpack this absolute divide across the nation. The heat wave in the west and the south is one thing to experience. But when you actually look at the historical data, it is not just unusual, it is record-shattering.
It's unprecedented.
The numbers we are seeing in the research are genuinely hard to process for late February and early March. For example, Falcon Dam, Texas. The data shows they hit 106 degrees Fahrenheit on February 26th. That is officially the hottest winter day ever recorded in the United States.
I think we need to pause and just let that sink in for a moment. 106 degrees
in winter.
In February. We are not talking about a pleasantly warm afternoon where you take off your jacket and enjoy the sun. We are talking about peak summer, dangerous heat indices occurring while the calendar still definitively says it is winter. This is heat that stresses the human body, it stresses local power grids, and completely tricks the local flora and fauna into thinking we are deep into July.
And reading through the notes, it becomes clear very quickly that this was not an isolated freak event for one single town.
No, not at all.
It is regional. Laredo, Texas hit 103 degrees, marking its hottest February day ever. Then you move over to California. Riverside reached 93 degrees, which completely obliterated a previous record that had stood since 1972. El Centro hit 96 degrees. So what is actually happening in the atmosphere to create a furnace like this in the winter?
When you look at the broader scope of the atmospheric data, this heat is a result of a persistent ridge of high pressure that has essentially parked itself over the western half of the country. To understand why high pressure equals extreme heat, you have to picture the air itself.
Okay.
A high-pressure system features sinking air. The atmosphere is literally pushing down toward the surface. As that air sinks lower and lower, the atmospheric pressure around it increases, which compresses the air.
And when you compress a gas, it heats up?
Precisely. It is basic thermodynamics.
Yeah.
As that massive column of air compresses, it dramatically warms up before it ever even reaches the ground. On top of that, sinking air suppresses cloud formation. It clears out the sky entirely.
So there's no shade.
Exactly, zero shade. So you have mechanically warmed air combined with a complete lack of cloud cover, allowing the sun to just mercilessly bake the surface day after day. For much of the western half of the country, this persistent setup has resulted in the warmest winter on record.
That unrelenting sunshine sounds great if you're on a beach vacation, but the research points out a massive, terrifying flip side to this persistent heat. While the 106-degree records are grabbing all the headlines, the notes emphasize a chronic lack of snow.
The snow drought, yes. From a meteorological and ecological standpoint, the lack of snow across the western United States is arguably the more dangerous long-term story hidden inside this heat wave. We are currently monitoring the worst snow drought in decades gripping the West.
I was reading through the impact reports on this, and it really struck me how this affects everyone, not just the ski resorts. The snowpack in the western mountains acts as a sort of frozen reservoir, right?
That is a brilliant way to visualize it. It is nature's water tower. In a normal, healthy winter, snow accumulates in the high elevations layer by layer. It stays frozen up there. Then as we move through spring and into the hot summer months, that massive snowpack slowly and steadily melts.
It feeds the whole system.
It does. That slow melt is the lifeblood of the West. It provides a consistent metered water supply that fills the rivers, supplies drinking water for millions of people, sustains massive agricultural operations, and spins the turbines for hydroelectric power.
So when we see a massive snow drought like we are seeing right now, that natural reservoir is virtually empty before the high-demand summer months even begin.
It creates a severe deficit. The cascading impacts are profound. The data shows how this immediately forces local governments to rethink water allocations. But the threat extends far beyond just drinking water. Think about the landscape.
The forests.
Right. Without that slow, steady moisture seeping into the soil throughout May and June, the deep forests and the low brush become completely parched incredibly early in the season.
It sounds like it is creating a giant tinderbox.
It absolutely is a tinderbox. The research points directly to a significantly increased vulnerability to severe, fast-moving wildfires. Because the vegetation dries out months earlier than usual, the wildfire season is artificially extended and intensified. And we cannot ignore the immediate economic devastation to winter tourism and recreation.
The ski towns.
Exactly. Entire mountain communities rely on that 3 or 4 month winter economy, the skiers, the snowboarders, the lodges, to survive for the entire year.
Right.
When the snow doesn't show up, those local economies collapse.
It is a devastating domino effect. Meanwhile, as the West bakes and waits for a snowpack that simply isn't coming, the East Coast is experiencing severe atmospheric whiplash. According to the data we are reviewing, the Northeast is currently digging out from a historic, paralyzing blizzard straight along the highly populated I-95 corridor.
The contrast is staggering when you view the country from a satellite perspective. You literally have people running emergency air conditioners to survive the heat in Texas, while thousands of miles away, people are completely snowed in, relying on snowplows and emergency services just to leave their neighborhoods in the Northeast.
And the really wild part in the research is that they are not out of the woods yet. The data indicates another round and possibly 2 more rounds of accumulating snow eyeing those exact same winter-weary regions this coming week. How does the atmosphere keep dumping heavy snow on the exact same spot in March while the rest of the country feels like July? The notes mention something called a Greenland block. I've never heard of that.
It is a fantastic meteorological concept. It comes down to a phenomenon known as atmospheric blocking. To picture this, imagine a fast-moving stream of water. If you drop a massive heavy boulder right into the middle of that stream, the water doesn't just push the boulder out of the way.
It has to go around.
Right. It's forced to divert entirely around it.
So the boulder dictates the flow of the entire stream.
Exactly. In the atmosphere right now, a massive, incredibly stubborn area of high pressure has set up shop near Greenland. That high pressure system is our atmospheric boulder. It is blocking the normal west to east progression of weather systems across the northern hemisphere.
It acts like a giant traffic barricade in the sky.
It forces the jet stream, which is that fast-moving river of air high up in the atmosphere that steers our weather to violently buckle. When the jet stream hits that Greenland block, it takes a deep, sharp dive southward right over the eastern United States. And as it dips down, it acts like a giant scoop, pulling frigid Arctic air straight down from Canada and funneling it directly into the northeast.
And because that Greenland block is so massive and stubborn, it just sits there.
That is the key. The pattern gets entirely stuck. The cold air continually flushes down into the northeast, interacting with coastal moisture to create these repeating blizzards, completely ignoring the fact that the calendar has turned to March. The weather systems are essentially trapped in a loop.
It is a phenomenal display of how deeply connected the global weather system is. A high-pressure system sitting over Greenland is the reason someone in Boston is shoveling their driveway for the third time this week, while a different high-pressure system bakes someone in California. But what is the actual engine driving this? Why is the jet stream suddenly acting so erratically?
To understand the mechanics of this madness, we have to look closely at the overall behavior of the jet stream right now. We just talked about how it dips around the Greenland block, but across the rest of the continent, the jet stream's personality is shifting. Instead of the deep, pronounced north-to-south waves that kept much of the country cold earlier in the winter, the jet stream over the west and central U.S. has become what meteorologists sometimes refer to as lazy.
A lazy jet stream, let's visualize that. How does a jet stream get lazy?
The best way to picture the jet stream is to imagine two people holding a long jumping rope. If you swing your arm wildly up and down, it creates deep rolling waves that travel down the rope.
Like big peaks and valleys.
Yes. In the atmosphere, an active, amplified jet stream has those massive plunging dips and huge upward ridges. That active wave pattern is what pulls cold air far to the south and pushes warm air far to the north.
But if you hold that jump rope and just barely wiggle your wrists, the rope stays relatively flat.
You've got it. A lazy jet stream flows much more directly west to east, moving straight across the country without those deep, dramatic north-south waves. It loses its amplitude.
And reading through the research, this west-to-east flow essentially acts like a giant atmospheric fence.
It does. A flat, lazy jet stream keeps the coldest Arctic air trapped far to the north in Canada. It acts as a barrier, preventing those frigid air masses from plunging down into the mid-latitudes. At the same time, because we are transitioning into spring, the jet stream naturally begins its seasonal retreat northward.
So the fence is moving north.
And as that boundary line shifts higher up into the continent, it opens the floodgates for the southern half of the United States. It allows that intense, unseasonable warmth from the southern latitudes and the tropics to just freely invade massive portions of the country unhindered. That is a major reason why we are seeing those 106-degree temperatures.
Here's where it gets really interesting, though. Looking at the data you brought in, there is a massive wild card currently in play that could completely upend that lazy jet stream. The meteorologists who compiled this research are heavily focused on an ongoing sudden stratospheric warming event.
Yes, sudden stratospheric warming, or an SSW. This is one of the most complex yet universally impactful phenomena in meteorology. To really grasp what an SSW is, we need to completely shift our perspective. We live, breathe, and experience all of our daily weather in the troposphere. That is the lowest layer of the Earth's atmosphere. But sitting directly above us is the stratosphere.
And the research notes that during the winter, high over the North Pole, there is a feature up in the stratosphere called the polar vortex. I know that term gets thrown around a lot on the news.
It does, often incorrectly.
Yeah.
The true stratospheric polar vortex is a massive swirling ring of exceptionally cold air and incredibly strong winds rotating counterclockwise high above the Arctic. The best way to conceptualize it is to think of a spinning top.
Like a toy top.
Right. As long as that top is spinning fast, it stays tight, centered, and incredibly stable. A strong, fast-spinning polar vortex keeps all that freezing, brutal Arctic air locked up tight right over the pole.
But a sudden stratospheric warming event throws a wrench into that system.
A massive wrench. During an SSW, the temperatures high up in the stratosphere can rapidly increase by tens of degrees in just a matter of days. It is a violent, sudden influx of heat. This sudden burst of thermal energy completely destabilizes our spinning top.
So it starts to wobble.
Exactly, it wobbles. The winds slow down. The polar vortex weakens, it stretches out of shape, and sometimes the core of it splits entirely into multiple, smaller vortices.
I'm trying to picture the consequences of that. If the vortex weakens and stretches out, it can no longer hold that Arctic air in place, right?
Under normal circumstances, that is exactly what happens. Meteorologists measure this stability using an index called the Arctic Oscillation, or the AO. When the polar vortex is strong and spinning fast, the AO is positive, and the cold air stays locked up north where it belongs. When an SSW event weakens the vortex, the AO typically flips to a negative phase.
So a negative AO means the cold air is escaping.
Think of it like a bowl filled with freezing water. If the bowl cracks or tips over, that frigid water spills out and plunges downward. A negative AO allows that brutal Arctic air to spill out of the polar regions and plunge deep into the mid-latitudes, spilling down into the United States, across Europe, and into Asia. It usually signals a massive late-season deep freeze.
But I'm looking at the charts here, and the research right now is showing something highly contradictory. Despite the fact that we are currently in the middle of a major sudden stratospheric warming event, the dynamical model guidance, the supercomputer forecasts, show a positive Arctic oscillation structure persistently hanging on.
And that contradiction is causing massive friction within the meteorological community right now. It is a fascinating standoff. The dynamical models, these incredibly advanced supercomputers calculating billions of atmospheric physics equations, are insisting that despite the warming in the stratosphere, the cold air will manage to stay locked up north. They are predicting the AO stays positive.
But history and the known physics of how an SSW operates say the exact opposite.
Yes, the historical climatology suggests that the bottom should eventually fall out. History tells us that we should see a massive delayed blast of Arctic air crashing down into the troposphere.
Yeah.
So you have the raw computer models and the historical climatology essentially in a bare-knuckle brawl.
They are completely fighting each other. And this must create immense uncertainty for anyone trying to predict the weather as we look toward late March. Will that warm, lazy jet stream hold its ground and keep the country baking? Or will the delayed effects of that stratospheric warming finally crash through the atmosphere and deliver a devastating late-season freeze?
It is the ultimate meteorological cliffhanger. As of right now, the data simply reflects a massive question mark for the end of the month.
While the late March temperatures remain a mystery we will just have to watch unfold, the immediate threats on the horizon are, unfortunately, very clear in this data. The research outlines a looming, multi-day severe weather threat targeting millions of Americans. It spans a massive geographical area across the South, stretching from Texas all the way up through the Great Lakes and into the Ohio Valley.
This is a scenario where we see the clash of these conflicting seasons turn violent. The ingredients coming together for this specific setup are classic, well-documented, and highly concerning for anyone in those regions.
Let's break down those ingredients. We have all this heat in the South, cold air trapped in the West, and storms trying to move through.
We talked earlier about the lazy jet stream. But as this new, powerful storm system begins to move inland from the Pacific, it changes the geometry of the atmosphere. We are seeing a pronounced, sharp, southward dip in the jet stream developing over the western U.S., perfectly paired with a massive northward bulge or ridge over the eastern U.S.
The research refers to this as creating an atmospheric highway. What does that mean in practical terms?
When you have a deep trough of low pressure in the west and a strong ridge of high pressure in the east, it creates a very steep, intense pressure gradient between the two. The atmosphere always wants to balance itself out, so air rushes from high pressure to low pressure. In this specific configuration, that rush of air forms a supercharged wind corridor, an atmospheric highway blowing straight from south to north.
And what is sitting directly south of this highway?
The Gulf of Mexico. That atmospheric highway acts like an industrial vacuum. It is actively, forcefully pulling incredibly warm, deeply moist air directly out of the Gulf of Mexico and surging it northward across the southern plains and into the Midwest. I really want to emphasize this point.
Please do.
The moisture drawn from the Gulf of Mexico is the primary, indispensable fuel source for almost all severe weather in the central and eastern United States. You cannot have explosive thunderstorms without that rich tropical moisture.
So we have this massive river of warm, wet air surging north, but it doesn't just sit there peacefully over Texas and Oklahoma.
Far from it. That warm, unstable air from the Gulf of Mexico is on a collision course. Remember that deep dip in the jet stream over the west? That dip is driving colder, much drier air aggressively eastward.
So you have two completely different air masses slamming into each other.
It is an atmospheric train wreck. Cold, dry air is incredibly dense and heavy. Warm, moist air is light and buoyant. When that dense, heavy cold front slams into the warm, unstable air fed by the Gulf of Mexico, the cold air acts like a physical wedge. It forces the warm, moist air to violently and rapidly rise into the atmosphere.
And that violent rising motion is what creates the severe storms. Looking at the data, it indicates a high probability for severe thunderstorms, large, damaging hail, and the potential for tornadoes across a massive swath of the country.
It is a textbook severe weather setup. It's nature finding the most violent way possible to balance out the extreme temperature differences we discussed earlier. And sadly, this perfectly aligns with the climatology of March.
I think we need to talk about that climatology because it might surprise some people. When I think of tornado season, my mind immediately goes to the movie Twister, to May or June out in the middle of Oklahoma or Kansas. But the data here highlights March as the true awakening of the season.
That is a very common misconception. While May certainly produces a massive number of tornadoes, March is incredibly volatile. Historically, states situated further south, places like Texas, Alabama, and Mississippi, actually see their highest frequency of tornadoes during the month of March.
Why is March so dangerous for the Deep South?
It comes down to transition. March is the transition point from winter to spring, which means it provides the maximum possible temperature contrasts. You still have powerful, roaring winter jet streams dipping south, bringing intense wind energy. But simultaneously, the sun angle is getting higher, and you begin to introduce that potent, summer-like heat and humidity creeping up from the Gulf of Mexico.
The clash of the titans.
Exactly. Furthermore, the wind shear in March is often incredibly strong. Wind shear is the changing of wind speed and direction as you go higher up in the atmosphere. That turning of the winds with height is what gives a thunderstorm the ability to rotate, and a rotating thunderstorm is what produces a tornado.
The research notes from last year provide a very sobering reminder of what this month is capable of. The data references a devastating outbreak last year where 90 tornadoes tore across 13 different states in March.
It is a critical reminder that the arrival of meteorological spring on March 1st is entirely synonymous with the start of severe weather season. The atmosphere is waking up. If you live in these areas, you cannot wait until May to prepare. You must have multiple ways to receive warnings and a solid plan in place right now.
Moving beyond the threat of wind, hail, and tornadoes, we have to look at the immense contrast of water that is currently forecast. This really highlights the extremes of the current map. On one hand, we have a significant widespread flood threat. Multiple ensemble models, which are basically a collection of different computer forecasts run together to find a consensus, are projecting high probabilities of 2 to 3.5 inches of rain across the Tennessee and Ohio valleys.
To a casual observer, 2 to 3 inches of rain over a couple of days might just sound like a gloomy weekend. It might not sound like a catastrophic amount of water, but in meteorology, context is absolutely everything. You have to look at the ground it is falling on.
The research brings up a metric used by the National Weather Service called flash flood guidance. How does that actually work?
Flash flood guidance is a highly localized calculation. The National Weather Service looks at a specific county or even a specific river basin and calculates exactly how much rain needs to fall over a 1-hour, 3-hour, or 6-hour period to initiate flash flooding. It takes into account the current soil moisture, the topography, and the local drainage capacity.
And the problem right now is the soil conditions in the Ohio and Tennessee valleys. The data shows some of these areas have been unseasonably dry.
When soil is deprived of moisture for an extended period, especially under an unseasonably warm sun, the surface bakes. It becomes hard, compacted, and incredibly resistant to absorbing water.
The term in the notes is that the soil becomes almost hydrophobic. It actively repels the water.
It does. It loses its porosity. So when you suddenly dump 3 inches of heavy rain onto baked, hard-packed earth, the water doesn't absorb into the ground like a sponge. It immediately pools and rushes over the surface. This leads to what hydrologists call excessive runoff.
And that runoff has to go somewhere.
It follows gravity. It rushes into street drains, small creeks, and streams. Because none of the water is being held back by the soil, those drainage systems are completely overwhelmed in a matter of hours, leading to rapid, dangerous flash flooding in areas you might not expect.
That is a massive threat for the Midwest and the South. But the research also notes that up in the Northeast, the flood threat isn't just coming from the rain falling from the sky.
No, the Northeast faces a very unique compounding threat. We just discussed the historic blizzards currently burying the I-95 corridor. Those blizzards are leaving behind a massive, incredibly deep snowpack. But the atmospheric blocking pattern won't last forever. As anomalous spring warmth inevitably pushes into the Northeast, accompanied by heavy spring rain, it threatens to rapidly melt that snow.
So you have rain falling from the clouds, plus millions of gallons of water locked in the snow suddenly turning liquid at the exact same time.
It is a double-barreled threat. When you combine heavy rain with a rapid temperature-driven snowmelt, the sheer volume of water entering the river system simultaneously is immense. The rivers swell rapidly, break their banks, and can cause widespread, catastrophic regional flooding.
It is an overwhelming abundance of water threatening the eastern half of the country. But if you look just a little bit further south, down to Florida, the picture painted by the data is terrifyingly dry.
The contrast in water distribution across the United States right now is stark. We're looking at massive flood threats in the valleys, yet the research clearly shows that 100% of the state of Florida is currently classified as being in a drought, every single county.
And the data specifies this is not just a mild early season dry spell. 67% of the state is classified as being an extreme drought.
Extreme drought means major crop losses are occurring, fire risk is extreme, and widespread water shortages are likely. The vegetation across the state is incredibly stressed.
And looking at the projected storm tracks for this massive multi-day severe weather threat we just discussed, the southeast might miss this rainfall entirely.
That is the cruel irony of the current atmospheric setup. The very same high-pressure ridge in the east that is acting like a wall, pulling the storms northward up that atmospheric highway, will likely keep Florida and much of the southeast entirely dry. The rain will essentially detour right around them.
Which leaves them incredibly vulnerable.
It drastically increases their spring wildfire risk. You have parched, dying vegetation, steadily rising spring temperatures, and absolutely no moisture relief in sight. If any dry lightning strikes occur, or if there is any human-caused spark like a discarded cigarette or a poorly managed campfire, the environment is absolutely primed for rapid, uncontrollable fire spread.
So what does this all mean when we zoom out? We have spent the first half of this deep dive looking at incredibly intense local disasters, 106 degrees in Texas, atmospheric blocking over Greenland, freezing Boston, hydrophobic soil in the Ohio Valley, and extreme drought in Florida. But the research insists that we look at the larger global drivers because the foundation beneath all of these local events is shifting.
To truly understand the global atmospheric picture, we have to look far away from the United States. We have to look down at the equatorial Pacific Ocean. Specifically, we have to examine the transition of the El Niño Southern Oscillation, or what meteorologists refer to as ENSO.
Based on the data, we have been under the influence of La Niña since roughly December 2024. But the research notes that this particular La Niña has been relatively weak and fairly short-lived compared to historical averages.
It has been underperforming, so to speak. And now, the data indicates it is officially fading away entirely. The latest projections from the National Oceanic and Atmospheric Administration, commonly referred to as NOAA, predict a 60% chance of transitioning into ENSO-neutral conditions between February and April of 2026.
So we are moving out of La Niña and into a neutral state, which often serves as a stepping stone toward El Niño. Before we talk about what neutral or El Niño means for the future of our weather patterns, let's touch on the history of these phenomena, because I was reading the background information in the sources, and the naming convention alone is fascinating.
It is one of my favorite pieces of meteorological history. It really shows how local observations eventually unlocked global scientific understanding.
The notes detail how, back in the 19th century, Peruvian and Ecuadorian fishermen noticed a strange pattern. Every few years, the ocean waters off their South American coasts would become unusually incredibly warm.
And for fishermen who rely on cold, nutrient-rich water to sustain the local fish populations, this anomalous warm water was devastating. It would completely disrupt the marine ecosystem, starving the fish and effectively ruining their crucial anchovy catch for the season.
Because this devastating warming trend typically peaked right around late December, the fishermen named the phenomenon El Niño, which translates from Spanish to the boy, or specifically the Christ child, in reference to Christmas.
It was a local term for a local economic disaster. It was only much, much later, as global climate science advanced and we began taking global temperature readings, that meteorologists realized this wasn't just a localized fishing problem in South America. They discovered it was actually a massive fluctuation in ocean temperatures that drives weather patterns across the entire planet. Once they understood that, scientists coined the term La Niña, which means the girl to represent the exact opposite phase, when those same equatorial Pacific waters become unusually cool.
Let's discuss the global impacts of these phases, particularly La Niña, since we are supposedly just coming out of one right now.
La Niña fundamentally alters the global atmospheric circulation patterns. When the waters in the eastern Pacific cool down, it alters where the massive thunderstorms form over the ocean. Typically, a La Niña event pushes the warmest water westward toward Asia. This shift alters the jet streams globally and typically brings significantly wetter, sometimes flood-inducing conditions to places like Australia, India, and Southeast Asia.
And conversely, the data shows it leads to much drier conditions across parts of South America.
Yes. And here in the United States, A La Niña winter often leads to a drier, warmer southern tier, which we certainly saw in Texas and Florida, and a wetter, colder northern tier. Though, as we've extensively discussed today with our broken weather map, the atmosphere doesn't always read the textbook.
But there is a critical, almost alarming data point in the research regarding this past La Nina. La Nina is fundamentally a cooling of the ocean, which generally translates to a net cooling effect on global average atmospheric temperatures.
It acts like a giant natural air conditioner for the planet.
Yet the data states that even with that vast expanse of cooler ocean water actively trying to chill the atmosphere, the year 2025 was still tied for the second or third hottest year on historical record globally.
That is a profound statement about the underlying, relentless warming trend of the entire climate system. Historically, a strong La Niña would guarantee a dip in global temperatures for the year. The fact that we just experienced one of the hottest years in human history during a La Niña phase means that the natural cooling cycle of the ocean is no longer powerful enough to mask the overall background warming of the planet.
And tracking this background warming has actually forced scientists to update the very metrics they use to define El Niño and La Niña. NOAA, the National Oceanic and Atmospheric Administration, has officially changed how they track ENSO.
This represents a major, necessary shift in scientific methodology. For decades, meteorologists relied on a metric called the Oceanic Niño Index, or the ONI. This old index worked by comparing the current 3-month average sea surface temperature in a specific patch of the Pacific against a historical 30-year average for that exact same geographical area.
But the research indicates a fatal flaw with that method in our current climate.
The fatal flaw is shifting baselines. The entire world's oceans are warming, and they're warming rapidly. If you were trying to determine if a specific patch of the Pacific is anomalously warm today, but you were comparing it to an average from the 1990s or 2000s when the ocean was already artificially warming, you get a skewed result.
It's like trying to measure if a pot of water on the stove is boiling by comparing it to how warm the water was 10 minutes ago, rather than comparing it to room temperature. The baseline is ruined.
That is a great analogy. Comparing warm water to water that was already warming means you drastically underestimate the true severity of the anomaly.
So what is the new metric that NOAA has adopted?
NOAA has transitioned to using the Relative Oceanic Niño Index, or ORNI. Instead of looking backward at corrupted historical averages, RNI is a dynamic, real-time measurement. It compares the temperature of the East Central Pacific to the temperature of the rest of the global tropics at this exact moment.
So it measures how much warmer or cooler the El Niño region is relative to the entire tropical ocean today, rather than decades ago.
Precisely. It filters out the background global warming to isolate the actual ENSO signal. It is a much more responsive, accurate way to track the mechanics of the climate in a rapidly changing world.
Speaking of a rapidly changing world, the research we were reviewing also briefly notes how broader environmental policies and governmental shifts impact the tracking, funding, and action regarding climate science. For instance, the data specifically mentions the EPA, the Environmental Protection Agency, revoking the endangerment finding regarding greenhouse gases.
That is a crucial piece of the broader context. When we look at this objectively, entirely separate from any political ideology or partisan debate, the revocation of the EPA endangerment finding represents a fundamental structural shift in how environmental policy interacts with climate science at the national level.
The research highlights that these regulatory changes have ripple effects.
Absolutely. Policy dictates resources. Shifts of this magnitude can vastly complicate the landscape of climate science. They can affect how meteorological research is funded, how tracking mechanisms like new satellites are deployed, and how national response strategies for extreme weather are developed, regardless of what the raw meteorological data on the ground is screaming. It is a reminder that the science of meteorology does not exist in a vacuum. It exists within a framework of human governance.
Our mission today is to stick to that data, and the data pointing toward the 5-year horizon is stark. Moving into the final section of our roadmap, the World Meteorological Organization, the WMO, alongside the UK's Met Office, has released research that truly pushes the bounds of what we thought was possible.
The statistics delivered in this WMO update are striking and, quite frankly, sobering. They are predicting a 98% chance that at least one of the next 5 years, specifically between 2023 and 2027, and the 5-year period as a whole, will be the warmest on historical record.
A 98% certainty in a meteorological forecast of that duration seems practically unheard of. Forecasting the weather next week is difficult enough.
It is incredibly rare to see that level of confidence in a long-range forecast. It speaks to the immense, undeniable momentum that is built up inside the climate system. We are looking at a powerful, compounding combination of factors. First, you have the steady, relentless accumulation of human-induced greenhouse gases trapping heat in the troposphere. That provides an ever-rising baseline of heat.
And then you combine that with the ENSO transition we just discussed.
Right. We combine that elevated baseline with the looming return of a warming El Niño event. If La Niña is the air conditioner, El Niño is the heater. El Niño naturally spikes global atmospheric temperatures. When you stack a powerful El Niño on top of the highest baseline temperatures in human history, you mathematically force the global average into completely uncharted territory.
If we connect this to the bigger picture, the research inevitably brings up the Paris Agreement and the famous 1.5 degrees Celsius threshold. This is a number we see in the headlines constantly.
It is, and this is a critical nuance that the WMO research goes out of its way to clarify. It is vital that we explain this carefully so as not to misrepresent the data. The WMO states there is a 66% likelihood that the annual average global temperature will exceed 1.5 degrees Celsius above pre-industrial levels for at least 1 year within this upcoming 5-year window.
When you hear that, it sounds like an admission of failure. It sounds like we have officially failed the core tenet of the Paris Agreement.
It absolutely sounds like it to the layperson, but scientifically and legally, we have not. The Paris Agreement's 1.5-degree threshold does not apply to a single rogue year. It refers to long-term, multi-decade climatological averages. Hitting or exceeding 1.5 degrees for one single, exceptionally hot El Niño year does not mean we have permanently breached the target or structurally failed the agreement.
That is an important distinction. However, reading between the lines of the data.
However, it is a massive, blaring alarm bell for the planet. It proves that we are now actively brushing up against a thermal limit that, just a decade ago, was considered a distant, worst-case scenario. It means that while the multi-decade average might not be there yet, we will be breaching that 1.5-degree level on a temporary basis with increasing compounding frequency in the years to come.
And the research makes it very clear that these temperature breaches will not be felt equally across the globe. The data points out very specific, disproportionate regional impacts that will alter global ecosystems.
The Arctic is the most glaring, urgent example in the data. The research notes that Arctic warming is currently happening at 3 times the global average rate.
Why is the Arctic warming so much faster than, say, the equator?
It is primarily due to a devastating feedback loop involving the loss of reflective sea ice. Ice is white. It reflects solar radiation back into space. Ocean water is dark. It absorbs solar radiation. As the Arctic warms, the ice melts, exposing more dark water. That dark water absorbs more heat from the sun, which in turn melts more ice, which exposes more water. It is a runaway acceleration.
The rainfall predictions outlined for this 5-year window are equally disruptive to the global status quo.
The shifting of global temperatures means the shifting of global precipitation. The WMO data suggests we will see significantly persistently wetter conditions in regions like the Sahel in Africa, Northern Europe, and Alaska.
But simultaneously, the data forecasts drastically reduced rainfall over other crucial regions.
Yes. We are looking at forecasts for severe, prolonged droughts over the Amazon basin and massive parts of Australia. I want to stress that these aren't just fascinating numbers on a meteorological chart. These represent massive, destabilizing shifts in global agriculture, water security, and ecosystem survival for billions of people and animals.
It's a lot to process, honestly. When you look at the totality of what we've discussed today, it's overwhelming.
This raises an important question, one that goes far beyond the raw meteorological data, the temperature records, and the computer models we've discussed today. When you step back and look at the sheer scale of these massive atmospheric swings, from 106-degree winter days in Texas to sudden, paralyzing blizzards in the Northeast, from entrenched La Niñas that still somehow produce record heat, to the looming threat of record-breaking El Niños pushing us past the 1.5-degree threshold, it becomes clear that the concept of normal weather is officially obsolete. The baseline has shifted entirely. The provocative question for you to consider as you digest this research is this: how do we, as individuals, as local communities, and as a global society, begin to design our lives, our infrastructure, and our daily routines around a baseline of constant, unpredictable atmospheric volatility? How do you build a resilient future when the sky above you outright refuses to follow the rules of the past?
You've been listening to Meteorology Matters, created by meteorologist Rob Jones. Thanks for listening, and remember, meteorology always matters.